Hello everyone and welcome back to the MASTA webinar series for 2019. My name is V and I'm from the marketing department here at SMT, and I'll be introducing our presenter shortly who will be hosting today's webinar. We've put together this webinar based on your requests for more information on the productivity of FE in MASTA. So we have Dr. Tom Harvey today who will be running through frequently asked questions on finite element. During the course of the session, you can expect to see areas covered such as housing mounts, torque transfer, bulk connections, advanced solver options, accelerometers, gear blank tuning, modeling, and more. Of course, if you have any questions, please send them through using the live chat box that you can see on your screen. And again, anything not covered, we'll obviously get back to you via our support team after the webinar has finished. I hope you can all see the screen, and thank you again for joining us today. We'll just take a few more minutes to allow for some more attendees to join us.
Hello everyone, I hope you can all hear me. So I'm Dr. Tom Harvey, as Via just introduced me. So I'm going to be going through some sort of frequently asked questions and hints and tips on FE functionality in MASTA. Yeah, please ask as many questions as you like. I'll try and answer everything I can during the webinar, but if not, we will get back to you. So this is just an outline of the main topics I'm going to cover today. So there's lots of different small topics today, and so hopefully there'll be something of interest to everyone. So first of all, I'm going through housing mounts, so how we can either ground or model sort of flexible mounts within a housing in FE mode. Then we'll go on to bolt connections, so how parts of FE are joined together. A topic that frustrates a few people is on torque transfer. So this is when we bring an FE model and it's not really working correctly how we expect. So I'll be giving a few hints and tips about how we can solve those problems. Talking about how to model accelerometers on your housing, the various ways we can add those in. We're talking a bit about gear blanks and kind of what levels of detail we should include for those, in particular about including the gear teeth. I'll be going through a few of the more advanced solver options, just touching on those to explain a bit more detail what some of those mean. And then finally, I'm going to explain the different modes that are reported in FE mode in MASTA and explain the difference between the different ones that you can see. And then finally, after that, I will, if we've got time, I'll just go through just to tell you a few of the future developments that we're going to be working on in terms of the FE functionality in MASTA in the future. So housing mounts. There's various ways of grounding your housing in MASTA. You can have rigid mounts or flexible mounts, and these can in turn be either defined in your FE program before you bring it into MASTA, or you can define them in MASTA itself if you have brought the full mesh in. For rigid mounts, you can define these wherever you find easiest, either in your FE or in MASTA. There's not any difference in what result you'll get. For flexible mounts, what we'd recommend is the sort of technique I'm going to show you in a few minutes is to define those flexible mounts within MASTA, because this makes additional results available. So we'd use a kind of rigid coupling component and use that to define the kind of flexible mount stiffness, and that lets us get results such as the forces, accelerations at the mounts, and also adjust the stiffness without having to redo the sort of FE condensation as well. So I'm just going to switch to MASTA and explain to you how we can set up those various options. So on the screen you should be able to see a kind of simple axle example that we have in MASTA. If I switch to the FE mode, we can see I've brought in the casing for the axle at the rear here. And for this axle we have two mounting points, one here and another on the right hand side over here as well. So these are the points where we want to ground this casing. So in reality we have some flexible coupling to the chassis. So first of all, the first method I'm going to show you is just making this rigid, so just grounding this within MASTA. There's two ways of doing that. There's one that's been around for a while. It's a bit awkward, and I'll show you an easier way in a minute. So there is some node selection functionality in MASTA. So you can switch the selection mode to node, and we can switch this option here to look at the surface nodes. I can either individually click on nodes now, or we can hold down shift and use a box select to grab those nodes. So we can grab nodes on the surface there, and then in the FE model details tab we can go to selected nodes, and from this drop down select fixed and click set this for all selected nodes. If we then use the show grounded nodes button and clear our selection, we can see that these nodes are now all grounded. The slightly easier method is to use the surface selection functionality in MASTA. So we can switch the surface. That lets us click on here to select all the element faces on a particular surface. It kind of automatically detects the corners to select that face, and then on the element faces tab we can then press ground, and that will ground that selected face, which is a lot easier than trying to pick the individual nodes. So that's the way we'd set up the grounding within MASTA if we wanted to ground them rigidly. But in this case what we actually want is to define some flexible mounts. So if I just clear this grounding from here, and here, so we can set these back to free in the same way as we grounded them. So we have a shaft hub connection here, which we can select. And I'm going to switch this to create a single node on one side. It doesn't really matter if you pick the inner or the outer for this. It's just going to be ground on the other side. We then see that we need to adjust that search region a bit just to grab the nodes on the surface there. So I'm just going to change that just to make sure that we include that whole surface. And so we can now see that we've grabbed all those nodes on the surface, and those will be connected to this node we've defined for the shaft hub connection. And now this casing is now going to be grounded via the stiffness that's defined on that shaft hub connection. We don't have to create the node in MASTA for this. We could instead, in your FE program, create a node at this location and then just connect that up in the standard way as well. That's another alternative. It doesn't really make any difference which way you do it. Then once you've done that and you've defined that connection for your two kind of flexible couplings, we can go in and define the stiffness for that. The simplest way is that we can define just sort of radial axial stiffness. You'll notice I've kind of aligned this already such that the axial direction is kind of up and down. So that lets you put in a different stiffness in that direction to the X and Y direction. You can instead switch that to specifying a matrix. If you've got a more complex definition of the stiffness for the component, then you can enter the stiffness matrix directly in here. And finally, we also have the option for a nonlinear stiffness. So this lets you put in the individual stiffness components versus position, for example. So this would let you model, for example, some kind of clearance in there. So you could have a gap before it became stiff. So we could say after 20 microns, the stiffness zooms upwards, for example, and that would let you model a clearance in there before it becomes stiff. So those are the various options. So there's quite a lot of flexibility in there. And once we've done that, we can then get the results on this mounting, which is particularly useful in kind of MVH simulation. If you want to know how much energy is going into the vehicle via those mounts, then you can use this method to figure that out. So the next kind of topic for today is bolt connections. So we often get asked about how to connect two parts of a housing together if in reality they've got some bolts between them. So there's a few different ways of doing this, and which method is appropriate kind of depends to some extent on the details of your particular casing design. So the first thing to note is that in MASTA we don't have any support for applying kind of bolt preloads, for example, or doing sort of contact analysis. So what you bring in must be sort of linear. So there's kind of three different levels of detail we can go into. The first is, I'll show you these in MASTA in a second as well. So the first is to just not worry about the bolts at all and just rigidly join the two surfaces that are going to be clamped together. This is the simplest approach, but in a lot of cases that is perfectly fine in terms of the overall stiffness in the casing. If you're not too interested in the details of close to that joint, then that can be appropriate. The kind of next level is, as before, you kind of rigidly join those surfaces together, but you also include some representative model for the bolts. So that's shown in the bottom right here. So the top right is just leaving a hole for the bolts in your kind of solid model, and we can also put a kind of bolt in that hole, and then we can also connect together the correct faces that would be attached in the FE in that case. And finally, we can do some kind of initial FE analysis to determine what kind of area is in contact, and I'll probably illustrate that in MASTA just to make that a bit clearer. So just before I show that, I just got a couple of questions that have come up on the mounting. So first of all, someone's asked about frequency dependent damping on a coupling. That's not something we offer at the moment. We have an additional modal damping factor that can get added, but that's not frequency dependent. It is just what it is. So that gives you some extra damping on that component proportional to the strain energy of that particular mode. And the other question we have is on the mount stiffness about whether we need to join the other side or not. So on the connections, on that component, I created a node on one side and I didn't do anything with the other side. So you can either leave that existing condensation node and it'll be ignored, or change it to none. That just makes things a bit neater. It won't make any difference to the final results. It's usually better to go through and just change it to none if you're not going to use a connection, just because it makes it a bit clearer that what you've set up and what you haven't set up. But it doesn't make any difference to your analysis. So for the bolted connections, if I just bring those example models into MASTA, so first of all, the simple case, where we got no bolt in there at all. What we have in here is a constraint defined between the surfaces. You can see we've got one contact pair. They're called contact pairs, but it's kind of a bonded surface in effect. So we just rigidly connected those two surfaces together, and that's it. The second model, we can see we've also got the shape of the bolt in there, so we haven't bothered going into detail the shape of the head or the screw thread or anything. We've just modeled it as kind of two cylinders effectively. So we've also introduced additional bonded connections for underneath the bolt head, and also where the thread is connected to the lower surface. And as before, we've still got the bonding between the two surfaces as well. And then in the final example, just like the previous one, we've connected the head to the upper plate and the thread to the lower one. But we've now defined a smaller area for the kind of rigid contact between the surfaces. And to determine what this would be, you could do some kind of initial preload analysis in your FE program. So yeah, you could apply your bolt preload and determine kind of which areas are going to be in contact and which are not, and then just join those bits together before you bring your FE into MASTA. The one thing to be careful of is that what's in contact may change during the analysis. So due to deformation of the casing, it may bring additional regions into contact. So you might want to go back and check once you've done your system deflection analysis. You might want to go back into your FE program and check that nothing additional is actually going to be pushed together by the bearing loads, for example. But that is kind of what you can do, but it is the most complex to get correct and accurate. So normally one of these earlier options is perfectly fine, and that will give you a good stiffness. The time when you really need to worry about it a bit more is if you're very concerned about doing sort of detailed stress analysis, for example, around your bolts, for example, and then you might want to go back and look into a bit more detail. But most of the time, you can kind of run your MASTA simulation, get your bearing forces, and then go on and do more detailed stress analysis later on. So the next topic today is on sort of torque transfer. So sometimes you might see errors such as this one shown below. So you'll find your system deflection fails, and it'll give you some error about your imported FE is not correctly transmitting torque, which is annoying. And I'm just going to explain what that is and various ways we can check and fix that. So first of all, to explain what the problem is. So your transmission and MASTA you're modeling is a rotating system. So a lot of FE is kind of just things that are not spinning around. They're just sitting there and deflecting, deforming under load. But we're trying to model things spinning around and transmitting torque. So this tends to involve quite big rotations of the components. So when we clamp the output, apply some load to the input, due to the kind of clearances and backlash in the system, it all tends to turn around quite a large amount, particularly if you've got some big long prop shaft or axle in your design. So any FE components we bring in to replace like gear blanks or those shafts need to have sort of good rigid body modes. So they need to be able to undergo large rotations without having any problems. And one bit of evidence for them not having good rigid body modes is that when you apply some torque to them, they don't transmit this properly. They lose some of that torque when you're applying it. It's not always obvious how to fix these because it can get quite into a lot of detail in terms of the details of the FE theory, and it can be quite sensitive to which particular FE program you're using. But we've tried to cover a few of the sort of common problems that we see in support questions in the next few slides. So first of all, to do with alignment of the model. So when you bring your FE into MASTA, we always have to line up the FE model with the MASTA model. And depending on your FE, particularly if you've got some kind of coupling in there that it has got some kind of 3 degrees of freedom, you need to make sure that the rotational axis is lining up with the FE rotational axis so that they're both in agreement. So if you're creating those nodes in the FE program, you need to make sure that those nodes are on the axis. And we always kind of recommend setting the origin of the FE to lie on the component axis with one of the primary axes aligned with the rotation axis as well. And to illustrate this, I've made another example of when it can go wrong. So this is a very simple model. I've just got a shaft with 2 bearings on it, and I'm then going to bring in some FE to represent a kind of simple coupling. So the first one I've just imported now is one that's okay. This is one's going to behave nicely and isn't going to show any problems. So if I just connect up these nodes with the bearings, then it will align the FE to the MASTA shaft, and if I just show you how this is connected together. So this is kind of represented coupling. So we've got a shaft in the middle here, some coupling in the middle here, and in the degrees of freedom here, we can see, so this first one is showing that we've got stiffness in the Y rotational component and in the X and Z translation. So it'll transmit torque, but it won't transmit any kind of tilting of the 2 shafts between them. We can run our condensation on this just to calculate the stiffness between those 2 bearing locations. Okay, yeah, I just had a question just to repeat the node alignment step. I'll go through that a bit slower in the next example. So we're going to show another example of that in a minute. So we've calculated the stiffness. We can now go onto the static analysis tab and kind of prod our FE to kind of check that we've got a good stiffness. So I'm going to manually do the kind of torque transfer check. That can be done automatically. So to do that, we select a node at one end and press ground to ground that node. Select the node at the other end, and I'm going to apply a torque in the y-axis, because that's the rotational axis of this FE, and I can apply 1,000 Newton meters to that, and then press solve. And we then get the results for the displacement and the force on the right hand side here. So we can see we've applied 1,000 Newton meters to one node, and we've got 1,000 Newton meters reacted at another node, which is exactly what you expect. That means everything is working as it should do. There is also a button down here, and that basically does that for you, but it's a lot more convenient for a complex model. So it will go through various pairs of nodes. So it'll go through the various axial nodes and kind of ground them in turn, and it'll apply a torque to other axial nodes and make sure that that torque is transmitted to that node. If you've got off-axis nodes, it will also apply tangential forces to those in order to check the kind of torque transmission as well. Yeah, so you also notice that we do get some X and Y and Z displacements here. That's probably because in this case I have set this to no stiffness at all in some of the tilt degrees of freedom, so it's not really very well constrained, this model, and you kind of avoid that in reality, and it wouldn't be a problem once we get into system deflection because we have a bearing on this end, so it wouldn't actually all fly apart like it is appearing to. If I now bring in a second version of this design, so I've made this quite an extreme example just to make sure it's clear. So the node at one end is correctly positioned. You notice the node at the other end is not in the right place. So that's the only difference between these two models, is that those two nodes are not correctly positioned. So I select my shaft to replace. I'm then going to connect the nodes up to the bearings as before. So we select one bearing, select one of the nodes. It doesn't really matter which way around we get them in this case. We go into the connections and press create link. And then we do the same for the other end. We select the bearing and select the other node, and again press create link. So by default, MASTA is doing an automatic alignment for the FE and these nodes. So it looks okay at this end because the node is in the center, but you can see at this other end that the kind of FE isn't really lying in the middle of that bearing, which is clearly wrong because it's put that node at the center of the bearing rather than the FE. And if we now calculate our stiffness again, then we can see what effect this has. So you can probably guess that because it's not aligned properly, when we apply that torque onto that node at one end, it's not going to actually be axial in terms of that FE component. It's going to be slightly off. So we're going to get some loss of the torque. So if I just press this torque transfer check button, we can now see that we got a failure. So applying that torque to one of the nodes and grounding the other one gave us the wrong torque. We can set those boundary conditions to check ourselves. We can see things have gone quite horribly wrong. It's all kind of flying to pieces. We've got some ginormous displacements here because we've got that zero stiffness in there, and yeah, it's a very badly defined problem now. In this case, I mean, the best thing to do would be to go back into FE and put this node in the right place. But we can also fix it manually. So we can manually line our FE model. So we know in this case that our y-axis is our axial direction of this FE. So we could instead switch to manual alignment, for example, and explicitly specify that FE position, or we can use the shaft alignment method. And for this, we now use the replace shaft as what we're aligning to. We can pick that our y-axis is our rotational axis, and then we can then set the correct offset in there to line that up. We then get a different error that there's a big radial error in terms of the node position, which is not that surprising because we know that was bad. So we can always just ignore that for now and increase that tolerance. If we now go back into our torque transfer check, it should now be okay. So even though those nodes aren't in the right place, the rotational axis is correctly aligned. So everything should be fine. In terms of this node being in the wrong place, it won't really matter in terms of other analyses. I mean, we allow some tolerance to be specified in terms of the positioning of the nodes, and we will then internally correct that position within the calculations so that that position of that node doesn't then have an adverse effect on the housing, for example, because there's always going to be a little bit of inaccuracy in those node positions. I mean, the only time that's not going to be the case is when if you create those nodes within MASTA, we'd always create them in exactly the right place that we want them to be, because we know exactly where we want the node to be for this bearing, so we can make it exactly there. But if they set up another FE program, there's typically going to be a little bit of error in that position. So we have to correct for that when we're sending the forces back to the FE in order to make sure we don't add any different additional forces or moments that shouldn't be there. So yeah, as I said, so if there is some problem with your node positions, it's important to check that your rotation axis is correctly lined up. Another place you can see that is if you go into the design mode and select the FE, you can also see in the report what the alignment is of that FE compared to your MASTA coordinate system. So you can see exactly how it's rotated relative to your world coordinate system. So you can also check there that it's got a nice alignment. Okay, so another common problem that we can get is to do with the sort of surface connections. So as I said, it needs to be linear in MASTA, so we'd always use a kind of bonded or tied connection depending on the FE program. You should also make sure that the two surfaces are as close together as possible, particularly if it's two parts of a shaft, so for example, a gear mounted on a sort of diff housing, for example, you kind of want those two cylindrical surfaces to be as close as possible together, because the nodes you're connecting have only got translational degrees of freedom. So if they're at different diameters, they will kind of transmit the same force but at a different diameter, which then results in a different torque on the other node. Some FE programs, when you're creating those connections, they have an option to adjust the nodes on the slave surface to lie on the master surface, and yeah, you should always turn that on, because that will get rid of some of that problem. And another thing that can affect is which surface is the master surface. So usually get an option of which surface is the master and which one is the slave. So sometimes if you swap those round, you'll find you'll get a better result. So that's another thing you can try. If you're getting an error, then you can try just swapping those surfaces over and seeing if that helps. Finally on this topic is weak springs. So in FE programs, as you saw in some of our examples we were just showing then, FE programs don't really like it if you've got degrees of freedom that are not constrained. So they try to help by getting rid of sort of rigid body motions. So one solution that they often has an option is to add weak springs to stop this rigid body motion and try and give you a better kind of static result. But that's not appropriate if you want kind of rigid body motion to be in there, which we do for replacing a shaft or a gear blank. So when we're calculating the reduced stiffness and mass, we don't want to include these. So you should make sure you turn this option off. And yeah, where that option is depends on the FE program, and their defaults again depends on the program. So it's just one other thing you should make sure you check before if you do have a problem. Next topic is accelerometers. So when you're, particularly for MVH, it's often helpful to compare results with accelerometer locations that you've got in your test. And there's two options for kind of how you define these. We can either use a single node, or we can get a group of nodes. It's usually better to do the second of these, so grabbing a group of nodes, because then you're kind of averaging over a small area, which is the same as what an accelerometer we're doing, because it's always going to have a finite area that you want to connect to. And we would also suggest connecting a point load to the node that you're adding, and because this lets you actually get results in a particular direction. So you can orientate your point load to match your accelerometer axes, and then you can exactly compare the results from MASTA to your test results. So first of all, if you want to do this within MASTA, the simple option of just grabbing a node, we can again do that with the node picking. So switch the selection mode to node, and I'd usually recommend turning on mesh as well. So it's best to use a corner node rather than a mid-side node on meshes, just because they can sometimes give slightly funny results. So we grab a node, go into selected nodes, and we can change the constraint type for that node to be condensation, and that will include that node in the results. The second approach is to add a point load. So you could grab a small surface in your FE program, and from there create a node, and then that would also be in MASTA again, or we can use MASTA to create the node as well. So if we just reposition this point load to be somewhere suitable. So for example, up the top here, then go back into the FE mode and tell it to create a single axial node for that point load. We'll then probably need to just fiddle about with the search region to just grab a little patch of nodes, and then yeah, we're done. So that'll create a node at that location on the housing connected to this little group of nodes. Because the z-axis of the point load is pointing this way, that is orientated normal to the surface of this housing, so that will let us get those acceleration results in that direction, in the normal direction. So for gear blank FE, one question we often get is kind of what level of detail to model these up to. So, I mean, first of all, should we include the teeth? And if we're including the teeth or not, if we're modeling it as cylinders, or what diameter should we go up to? So first of all, for teeth, there's a couple of situations where you should put these in there. So if you've got a thin rim or a thin annulus, for example, the stiffness of those teeth could be quite important for how stiff that ring is, and so in that case we would say to include those. Another situation is if you're doing MVH and your teeth are quite significant in terms of the mass and inertia of your gear blank, then again, in that situation, you want to include those, because otherwise it's the best way to get that to be accurate. There is various alternatives if you're not including the teeth to try and get the mass and inertia right, but it's not quite so easy. So you'd have to either set the diameter of that cylinder to try and account for that mass and inertia, or you could change the density either locally close to the outside or for the whole gear blank in order to match the mass and inertia to what it should be for the gear with the teeth. If you are including the teeth, then one important thing is to not connect to the surface of the teeth. So you might be tempted to put the node connected to the tooth flanks. We wouldn't recommend that, because the mesh stiffness we put into MASTA from ISO or from the LTCA calculations, that includes a factor for the bending of the teeth. So if you're connecting to the surface of the teeth, then you'll be double counting that. So we don't want to do that. So we'd always connect those nodes to a kind of surface of nodes at the root diameter, and that should be within the FE. So you want to grab a kind of set of nodes underneath the teeth rather than on top of the teeth. So if I have a model up here that we've done that already in. So this is a ring gear, so this has got spline teeth and the gear teeth all in it. So you can see we have our teeth here. We have connected to this kind of surface of nodes at the root diameter underneath here. It will default to doing that automatically. One setting you should change is there's a setting for has teeth. So on this geared connection, we've checked the has teeth option, and that will automatically change the defaults for example, which nodes to pick. So change it to solid nodes rather than surface nodes, so that it's picking up nodes within that FE solid rather than just picking up nodes on the surface. In terms of the span of the patch as well, we have a default for that as well. So by default, this is to cover a kind of, it's related to the contact ratio to cover the kind of section of the gear that would be in contact sort of over a tooth pass, because that is the kind of area over which the force would be distributed. So you'll notice that the patch doesn't follow the helix angle here. This is kind of the kind of area that would be in contact from if you were to run the tooth contact analysis. So you'd get a few contact lines that would kind of cover a rectangular area rather than covering a sort of helical area. Okay, so, and if you're not including teeth, then we'd normally model the gear up to the root diameter. And this is because that's kind of gives you the least stiffness in your gear blank, and so it gives you the worst misalignments. So it's kind of a worst case really, rather than being the closest to reality. Just going to go through a couple of more advanced options that we have in the solver. So the first one that we often mentioning to people is out of core solver. So if you're finding you're restricted in how much memory you have to run your FE condensation within MASTA, so we have an option to run out of core. This is slower because it's got to write to the hard disk rather than doing all the calculation within your kind of local memory of the gears. So we'd recommend always using a fast SSD with plenty of space as your kind of disk for writing this to. The options for this can be found on the mass and stiffness tab. So under advanced solver options, you've got use out of core. If we check that box, then you can then specify a folder. So it defaults to some local temporary directory, and you can check this box if you want to specify an alternative location. So if you've got a particular disk you want to use. So just another question about gear teeth and whether we include them for bevel or hypoid gears as well. And yeah, I'd say the considerations are kind of similar for cylindrical gears really. It depends on kind of how thick your gear is really, and whether that stiffness of those teeth is adding some significant stiffness to the bending of that gear. But again, the same applies, that we'd connect to solid nodes underneath the teeth, not to those teeth surfaces. Another option under advanced solver is the MPC type. So the default is the matrix transformation method. This is the most accurate one. This will enforce the constraints by eliminating degrees of freedom, which results in a smaller problem, which is better. But it's not always possible. If you've got more than one constraint that is sharing nodes, then it's not always possible to do this process. So in that case, we have to switch to the alternative, which is the penalty function method. And this uses a large stiffness instead in order to enforce those constraints. This does reduce accuracy slightly, but it's usually not much different, and it is a bit more reliable than the other method. You can use it in more situations. If you have kind of failure and switching this would help, then we do try and detect that and warn you about it. So that is kind of what that message means. So the final section for today is just to explain the different types of modes that we report in the FE mode in MASTA. I'll show these in the interface in a second as well. So the first of these is the internal modes. So these are part of the CMS method in order to improve the approximation of the reduced mass matrix. In the method that we use in MASTA, and is usually the default in most FE packages, these are calculated by grounding the physical condensation nodes. These are entirely part of the approximation method. They're not kind of used for anything else apart from that. On the mode analysis tab, we also have two other sets of modes. The first of these is the reduced model modes. These are calculated from the reduced stiffness and mass matrices, and those are kind of showing the approximation of the modes of the full FE model. We also have the option to calculate the modes of the full FE model as well. And ideally, we'd like the reduced models modes and the full FE model modes to match up to some frequency of interest. And if they don't, then that's when we then add more of the internal modes. So if we just open this model again, so internal modes show up in this tab here. We've got none calculated at the moment for this model. We can use the options here to calculate those. On the mode analysis tab, it will first show you the frequencies of the reduced model. So we've got 24 in this case because we've got 24 degrees of freedom in our model. And these are calculated based on this mass and this stiffness matrix that we've calculated within MASTA. We can press the calculate button here to calculate the modes of the full FE model as well. And it will then do a comparison of the two once it's done that calculation. Just while that's running, I'll just answer one other question that's come up. So for the T calculation, so if you're using the basic or advanced LTCA, yeah, MASTA will ignore the teeth in your FE model, and it uses a separate mesh or a separate stiffness for that LTCA calculation. As I'll show in a second on the final slide, that is something we're working on improving in the future for MASTA, to try and share the same FE model for doing the T calculation with the deflection calculation. So yeah, it's being a bit slow at the moment. I think it's tired from this WebEx. So if I just run through quickly this what we're working on in the future for FE as well. So there's a couple of new features in MASTA 10 coming up. So the first of these is the option to mesh gear teeth in MASTA. So this is available when you're using the shaft geometry meshing within MASTA, or also when you're importing a gear blank. So you can import a mesh of your gear blank into MASTA and have MASTA generate a mesh of the teeth and attach those two together. The second thing coming in MASTA 10 is being able to save your external full FE model in multiple files rather than just a single file at the moment. So this separates out the mesh and the settings and the reduced matrices from the expansion vectors. So the expansion vectors are the large part of the external file at the moment. So these are used for just calculating the deformed shape, or for quickly calculating the stress or the radiated sound power. So they're not required if you want to just make some changes or just look at what your FE looks like. So we've separated those out into separate files. And other things we're working on for a future release is, as I mentioned, sort of a closer coupling between FE and LTCA. So sharing that same model for the two. We're also looking into sort of simplifying the creation of things like mounts and accelerometers from the FE model. So without having to create components in MASTA and move them manually to the right location and orientation, we got some ideas for how to help that. And also an option to unload FE as well. So we find, yeah, some of our customers have been saying that they load in a bunch of FE, look at some results, but then they're running out of memory and they want to recalculate something, so they want to unload that again. So yeah, we're adding those options in there. So this is run now, so we can see our reduced frequencies, our full frequencies, and the difference. So we can see that these don't match up. So this reduced mass matrix is not very good at the moment. The stiffness is, you don't have to worry about this comparison if you're just running a static simulation, because the stiffness is always exact. But if you're running MVH, then these modes you really want to match up. I mean, if you're interested in MVH up to say 4 kilohertz, you'd really want this matching up to 8 or so in order to be kind of confident in the results. So when you see some results like this, where you've got some big errors between these modes, you then want to go back and re-reduce this with more internal modes to improve the accuracy. Okay, so I think that's about all we got time for today. So I had to speed up a little bit at the end there, but just final thing to say is that the next webinar coming up is 1 month yesterday, so 18th of July, and that's going to be looking at an overview of the features coming in MASTA 10, which is going to be released within the next month or so. So I hope you'll all sign up for that once the invitation goes out, and I hope you've enjoyed today. I think I've answered most of your questions that have come in during the webinar, but if you want any more details on those, then please just drop an email through to support, and yeah, we're happy to answer any questions or share any examples that I've looked at today. And yeah, I hope you've enjoyed it all and learned something useful. Thank you for your time.